Hello, my name is Wayne Strasser from Liberty University. I'll be discussing today accelerating chemical reactor design by leveraging fuzzy logic PID controllers. For the most part, this work was carried out by my graduate student Eric Turman, who's now at General Motors, and the work is brought to you by my group, FLUID, which stands for Flow at Liberty University for Innovation and Design. Our reactor is a low-density polyethylene autoclave shown in the upper left-hand corner. A close-up of one of the zones, an oblique view, showing the catalyst plume being injected on the left-hand side. The plume is outlined in colors from blue to red, meaning cold to hot. The range is purposely undisclosed because of the proprietary nature of the reactor. But in general, this is a polymerization system, exothermic with a heat source. We have a rotating stirrer shaft that has complex paddles and baffles. The geometry itself is convoluted in the sense that there are near wall features that create local shear and turbulence. And throughout the reactor, there are 4 zones, but 5 independent PID controllers, both in the plant and in CFD, to match the plant, maintain thermal stability by making adjustments we'll be discussing. Well, validating CFD is expensive and time consuming. The bottom of the page on the right shows a time plot, time series, where we're looking at temperature expressed as an error being a difference from set point, where -7 to 7 degree differentiation. On the left-hand side of this plot, we've made a time step change to evaluate time step independence. And we've marked there on the right-hand side of that section a QSS, meaning quasi-steady state, the region over which we were interested after we made the time step change. Because the reactor was continuing to change from 0 to approximately, let's say, 130, that last little bit of time was what we considered QSS was useful for us. On the right-hand side of that same plot is a mesh refinement study in addition to the time step change, and you see that the controllers received a disruption from the set point, so they made their adjustments, and you see that the region on the right-hand side, small region of quasi-steady state, is all that was useful. So of that, let's say 280 seconds of runtime, 280 flow seconds, only about 10% was useful for the data we needed in terms of being quasi-steady state. For those not familiar with PID control, we'll give a brief overview here. The process first on the left-hand side of this plot is a comparison of the measured data from the plant, which is output shown on the right, is fed back to the input, and that's compared to the set point in that first circle. And that produces an error, not an error of deviation between experiment and CFD, but just a deviation between the measured value that we want and the set point that we want. From that error, you move into a block of 3 considerations, and then an adjustment's made, and that information sent to the manipulated variable in the process, and then that produces an output, and the cycle continues. Those 3 constants are linear gain, integral gain, and derivative gain. The equation, which is the velocity PID algorithm, is not shown here. But in general, linear gain makes adjustments based on the ratio of set point, or sorry, the ratio of error. The integral gain adjusts for how long the error has been in play, and the derivative gain makes some adjustments based on how rapidly the error is approaching 0. So how PID works in our current reactor, we're going to focus on zone 1 only. And in zone 1, there's an inlet on the left, an outlet on the right, and downstream of this on the right are other zones actually attached to zone 1, but they're not shown for simplification purposes. There is a stirrer shaft, and on the left-hand side is the thermocouple, which is TC. And how this works is these 3 controllers, they alter reaction rates in these 3 regions, and the purpose is to address this error issue, which means the set point of that thermocouple minus the spatial and time average temperature across that tip. Then based on that information, we manipulate the chemistry. We modify the constant in the Arrhenius expression, the termination constant shown as A sub T on the right-hand side. And this was discussed extensively in our APS presentation in 2020. So we're controlling chemistry constants instead of controlling the catalyst speeds, which is what they do in the plant. And Eric discussed this in 2020, and it's It's a little bit confusing as to why we do this, but it's actually better to do that when we have the latitude to adjust constants in CFD. Of course, in real life, you can't adjust constants. But we do that in CFD. It's better for two reasons. First is when you make a controller change, instead of waiting for the catalyst to enter, which is what they would control in the plant, instead of waiting for that to enter and mix its way into the zone, by adjusting a chemical constant, you affect the entire zone you're controlling all instantaneously. And the other reason is we know what the catalyst flows should be, but there's a lot of uncertainty associated with the Arrhenius expression. If you look up A sub t in the literature, there's a wide range of variables that are considered acceptable. Since the uncertainty is mostly in that reaction, more than it is in the catalyst feeds, we figure it's better to go with the item that has the most uncertainty, so we adjust the chemistry. So the way the fuzzy logic process works in these 4 steps, first we receive the crisp input, and this is embedded within the PID control we'll show on the next slide. But we receive a crisp input, and that's the measured variable from the system, and we can receive multiple inputs. Then we do a fuzzification step, and that's we translate these crisp inputs to a fuzzy variable, and we'll describe that upcoming shortly. Then we consider rules, and these are stored rules to determine the output based on if-then statements. Then we have to defuzzify that to convert that to a crisp output so that our process can use it. In translating to fuzzy variables, we consider membership functions. And instead of, again, being a crisp variable, you now have very hot, hot, and warm instead of just too hot, or cool and very cold instead of just, okay, this is too low. And the degree of membership is based on this membership function. We'll describe more on the next slide. The output of the if-then statements is we can bring in multiple inputs, and if input 1 is X and input 2 matches criteria Y, then output C. So the membership functions take on multiple shapes. We can use triangular, trapezoidal, Gaussian in the upper left-hand corner. And the way this works is these are comprised of the fuzzy sets. The range of inputs is on the x-axis, so the fuzzified inputs coming in. And then the degree of membership is on the y-axis, either 0 or 1. But again, there's a range, so it's not a one or all. And these can be tuned. There's various types of membership functions as shown here. We can select the number of fuzzy sets. We can define the input ranges. Then we have to make a decision based on the center of the fuzzy sets. In this case, it's shown as P2. And then we have this nonlinear variable gamma. It's important. We found it in our work to be extremely important in terms of convergence, but that's beyond the scope of our talk today. And in the fuzzy sets, the decisions based on the colors of the lines and the membership functions match the color in the text in the fuzzy set box in the upper right-hand corner. You either have a very negative big, negative, 0, or positive and positive big. Again, this is a range of variables instead of just a go, no-go. And this nonlinear factor I mentioned a second ago controls how quickly you or how much you weight moving from left to right across the x-axis to the various sets. So a gamma of less than 1, say on the bottom right-hand corner, a lot more weight is given to the variation on the sides on the outermost boundaries, whereas a gamma greater than 1 has a lot more variation along the center point, as shown in P2. Now let's take a broader view as to why we're doing this and the benefits of fuzzy logic over PID. So the PID control is shown on the left-hand side. We've got the output on one axis, the change in error, and then the current error on the third axis. And we see a plane. This is a linear control method. We can tune 3 gains. We only have access to those 3 gains, which is the main gain, integral, and reset. Integral and derivative. And this is proven and robust, so we know that PID works. However, now enter fuzzy logic PID control. This is a nonlinear method, as you see in the planar system is now containing curvature, and you can tune numerous metrics, and that's good and it's bad. It's good that in that you have more levers to pull. It's bad in that now you have more tuning to worry about. But past work does show that fuzzy logic and PID is a better combination and faster than PID alone. Now let's look at the control structure and the overall flow of the process. Our CFD model outputs the moving time average which is a spatiotemporal average of the thermocouple temperature, and that's our main outgoing information. And as you recall from earlier, we compare that CFD value to the set point, what we want the thermocouple to be, and that gives us E and E dot, which are the crisp errors and the crisp error derivative. We feed that now to our membership functions to consider fuzzy logic to adjust our gains. We're going to adjust the main gain, K sub C, and the derivative gain, tau sub D. We're going to look at the current error in the upper left-hand corner, the error derivative in the right-hand corner, both triangular membership functions. And we say, if input 1 is X, which is the current error, and input 2 is Y, which is the error derivative, then we have an output Z, and that is our gain information, our fuzzy inputs, EF and E dot F, and our new gains, our updated gains. That goes to the fuzzy logic controller, and we introduce three options. First, if the error is positive big and the derivative is less than 0, we have a clamping function on the manipulated variable A sub t. Or on the other side, if error is negative big and the derivative is greater than 0, then we have a clamping function to increase A sub t. And then in the center, if those conditions are not met, we revert to the PID controller, the baseline. Now to the good stuff. These are all three controllers in zone 1, which is only the thing we're focused on now. The response of them to our final tuned system of a 50% increase in catalyst feed at time equals 0. On the left, the first plot is the controller 1, second plot is 4, and third plot is controller 5. And these are just arbitrary nomenclature from the sponsor, but they are three positions in zone 1. You see fuzzy logic is in solid, and the PID for each one is in dotted and dashed lines, I guess. And you see in all cases, the fuzzy logic has the least overshoot, the least undershoot, and the most quickly reaching quasi-steady state. So here are our data. On the left-hand side is fuzzy logic PID for the three controllers. We have a settling time of 50, 60 seconds in that range, the percentage overshoot, and the total integral of the error we experienced during the time. PID controls on the right, much higher settling times, much larger overshoots, and a dramatically larger integral of error. So what we found was that the fuzzy logic PID control was 54% faster than PID in terms of CFD convergence. So this is a huge win, great time savings when it comes to CFD. It's a great cost savings when it comes to using cloud computing, should that be your choice of CFD computing, and even for the plant, should they want to implement something like this. And as we see what happens to the actual outputs, again, this is the manipulated variable, which is A sub t. In all cases, 0 to 1 represents the range over which A sub t was modified. And then 0 to 1 on the x-axis is the normalized flow time. Time equals 0, start of the test. Time equals 1 is the controller settling time. So they're going to be all settling at 1 because we've normalized them that way. And the rise time is the time it takes for the controller to increase from 10 to 90% of the final value. You see all the fuzzy logic PID controllers, rise times occur within one decision or one controller point, which is about 3 seconds. And the PID controller, the rise time, those took in the range of 3 to 7 control decisions. So the final A sub t for the fuzzy logic and the PID are within 2% of one another, which means our programming is correct because we do expect them to reach the same value. So in conclusion, the fuzzy logic PID control proved to be 54% faster in convergence. This produced lower overshoots, which is a big deal because it's potential for hotspots in the reactor should you have a catalyst feed excursion. Hotspots lead to runaway reactions, which is a topic of one of our papers. Significantly lowered the rise time. And the important feature of this is that everything we programmed here, all the benefits of fuzzy logic, don't cost anything extra in solver time. So we're not solving enough additional variables to actually make a difference in our compute time. In fact, we have nothing but savings. So I'm interested in entertaining questions. Here are references for this work shown on the left-hand side.